All right. Thank you guys for coming. My name's Tuff. I am the data scientist at ESEL and Earth Lab, and this will be a 2-week, two-part series. This week is more background, context, philosophy, me just sort of talking about the topic. Next week will be about application. So we'll do some prompt engineering, how to do multi-agent things, how to sort of piece these together and use them in real world. But today, the idea is just to get our background and get all aligned on the same page. I gave a talk about 3 months ago called AI for Teachers, and I'm going to try to not repeat a bunch of stuff from there. So if you feel like you're missing some stuff or this is missing stuff, maybe go back to that and get some of the precursors that I talked about. But this should be self-contained. You don't need to have seen that other one, but just know it exists. So part one is about this mental model. How do we as researchers think about AI as a collaborator? What is it good at? What is it bad at? So let's just start. This was in Science last month. And it says from the 1980s, so they looked at all these papers and all these GitHub repos since the start of the 1980s. Scientific papers that use AI have drawn nearly twice as many citations per year. Researchers who adopted AI have 3 times as many papers and received 5 times as many citations as their non-AI using peers. Junior scientists who embraced AI were also less likely to leave academia and more likely to advance into established research roles. That's quite a statement, right? So this was from a news article from a Nature paper. Here's the actual Nature paper. I skipped to figure 2 because it's about the citations and the academic survival. But you can see the AI is in red and the non-AI is in blue. And so AI papers, again, this is over 30 years of publication. AI papers got more citations to begin with and maintained this flatter. They didn't drop off as much over time, over 30 years. Across different disciplines, you see the number of citations per researcher was something in that 5 times order. So for biology, my home, the average researcher gets 15 to 20 citations a year. If you have AI, it's something along the lines of 75. Over here, we have academic survival. So for individual disciplines, the top one is your probability of dropping out, and this is your inverse probability of establishing yourself as a scientist. Across all of these except geology, there was an AI penalty in geology. So apparently AI has not figured out the rock game very well yet. But for a lot of the other ones, you see this somewhere in the range of a 25% gain for having used AI in terms of how quickly you get established. So this graph over here is a timeline towards establishment, and you're seeing red is steeper. Red are getting promotions faster, getting faculty jobs faster, getting promotions faster than non-AI people. Again, this is over a 30-year time span. Separate study that was included in those stats, but this is just code. So the previous ones were like citations and publications. This one is code that was produced. First, let's see the United States versus other countries. We got this 1 or 2 year head start, largely from Copilot. So Copilot was released in the United States and not released internationally. And it was the first time people really started using code, using AI to write code for them. You get another big jolt, and it's across the world when GP3 comes out. And then we start moving into these multi-agent models that are specific for coding, and you're starting to get more and more adoption. So the US was the early adopter, and they continue to have the highest AI use of code, of using AI to generate code. A lot of other countries are catching up. Notably, China is low on here, but there are a couple things, right? They are going to be using different native languages on GitHub. The algorithms of this particular study are going to definitely be underrepresenting Chinese contributions here. But you see a lot of the other contributions doing the same thing. From though, over here, they said, okay, can we divide this by where you are in your career? And so we have first benefits. So who benefited? The average benefit of using AI to generate your code professionally was about a 3.6% increase in producing code that worked, producing code that eventually got published and they got distributed. The real divide here, though, is we look at the yellow versus the green. The yellow are senior scientists and the green are junior scientists. So senior scientists actually saw a 6.2% increase in their productivity, and they make up for the entire average. Junior scientists found no benefit, even though they used AI more and they trusted AI more, they found no benefit in the amount of code that they produced or how well that code produced. So here we're seeing this major signal of a future digital divide coming, and something that will heavily impact our future careers as the senior scientists sort of accelerate away and the junior scientists are left behind. A lot of this is you think they don't know what to do yet. So they don't, you can ask the LLM certain questions, but the LLM does not have a career's worth of breadth of knowledge to know what comes next or what the new frontiers are after where you're at. It sort of has this limited context window of where you're at and where you could go. And that's stifling these juniors. So we have a lot of work to do in training. And I think this shows that the sort of classic academic mentor model is alive and well. And we sort of need it more than ever in an LLM world. These other two are this constriction of breadth of knowledge across these users. So these are senior users still largely represented here. And first topic breadth went down almost 5%, and engagement with the literature went down 22%. So people are diving into the LLM and using the LLM to go deeper instead of wider into their topics. And so they're looking at fewer different types of literature as they're investigating. They're more reliant on a few publications that they really like. And so you see this constriction. We have some other plots that we'll look at later. Okay, so that's our trend. So that's sort of me trying to sell you on this is actually making a pretty big impact on science. If you're doing it right, it is a major productivity boost for people. And if you're doing it wrong, it sort of wastes your time in a lot of ways. So doing this properly, I think, makes a big difference. And we should take some time to think about that. So here's our context. We are jumping into some theory. This is a flight map. When I first started here, I had to go take the drone class. Some of you have had to take the drone class. And you have to learn how to read these crazy things. And it's really hard, but it gives you everything that you possibly know to fly over New Orleans without crashing into anything or flying into any illegal places. And you can do this regardless of where you're from. This is what we call a symbolic artifact. We're eventually going to get to how AI is sort of a modern incarnation of a symbolic artifact, what they are. But it essentially is something that we create as a culture to help transmit information. So this is a cultural training apparatus. So our culture has made this training figure for us. We can look at this map, use that map, and do all of this stuff that we hadn't been able to do before. And it does a couple things, and we're gonna talk about how AI builds all three of these things really nicely. One is its memory. So this is largely the function. David Krakauer from Santa Fe Institute talks about this evolutionary trend towards persistent memory. So through all of evolutionary history, you see these things being built to help memory stay around for a little while. So you get brains, you get collective intelligence, you get ant colonies, all the way up through things like the sextant and to measure latitude and longitude and maps, algorithms, models that we use. These are all things that our culture has collapsed and condensed into a training module for us that we can take and learn and use. Amplification. This amplifies one person's ability. So one person now has the ability to fly a plane through a very complex situation and know everything that they need to know. Their power is now amplified. Their intelligence is now amplified because of it. And prediction. This allows you to see into the future and know, like, in 6 months, I could fly here and here, or in 2 years, I could fly here and here. I would know the scheduling of when I could fly because of this thing that was built for us. So we're going to break that down into an actual mental model that helps us understand AI and how to use it. So Act 1 is going to be what we call the intelligence ladder. This is how we get those memories, how we store memories. 2, compression scaling. This is how we get amplification of these tools. And finally, the prediction part, which is this long history of autoregression that we've been using. So Act 1, the intelligence ladder. This again comes this same thought that I was just talking about with Krakauer. that intelligence at some point moved outside of us. So lots of organisms have developed intelligence of some sort, and they build these things to formalize and institutionalize some memory outside of themselves. This gives lots and lots of things. There's a long list of things that you could think of. Pretty much any invention in human history can go into these categories, and they over time get more and more complex and help us do more and more complex things and take more and more effort to use and more effort to build. So there are lots of trends over time of these things. Krakauer makes a big distinction, though, between complementary and competitive artifacts. And so he would say something like a map is complementary. You can take a map and show it to somebody that's arrived in Boulder. You can show them a map of Boulder. They can look at that, get the lay of the land, and then theoretically never have to look at that map again. You've taken that knowledge and implanted it straight in their brain. It's now useful training data that they can use to do other things. A competitive version of that would be GIS navigation, where you've stopped learning where to go and instead just listening to a set of instructions. And so the GIS would be a competitive cognitive artifact in that it helps you do all these things, but your brain stops doing that because something else is doing it for it. So we talk about how these come about. We get some new start of some new situation. Let's say there's language. We now start a new language. You get this big expansive part where everybody explores the variance of what you could do. So it's what kind of words could we make up? How do words come together? What order of words do I use? Which one, if there are multiple words that mean the same-ish thing, which one do I prefer in which context? And people experiment. They do all kinds of different things. And then eventually we collapse down into some cultural norms of things when finally people start to agree on this. So for something like language, we can think this took somewhere on the order of 10,000 years, right? If you think about slightly before that in terms of like genes and heritability, that was something on the line of 10 million years. And if you go even before that to like just cellular metabolism, you get something like 100 million years, right? So these are condensing time scales as we're going through. But the whole idea is you start some new exploration of a thing. There's this big variance of exploration, and then it collapses down. So presumably, we're going to get to where we're talking about AI as one of these things that collapses, but then AI also doing these things on its own. Through history, every single time we get one of these collapses, people freak out a little bit. And it was pretty fun. I wish that I could list all like 1,000 of these quotes for everything that everyone was scared of. But here we have Socrates and Plato were both like freaked out about the new invention of writing. And how like this new writing thing was going to mean nobody remembered anything. They were going to externalize everything that they had ever heard. Who in the world was going to read all of this stuff? And that like the demise of the human condition was this invention of writing. We can go to when at the printing press in the mid 1500s. Now all of a sudden there was a real concern that like writing was getting out of hand and books were going to just be there were just too many books and no one person could read all of them. And we're just going to be weighed down by the collective weight of all of this writing that we had made. And then all the way to 2008, we get lots of exposés. And there were sort of like 4 or 5 years where everybody was writing about how Google was making everyone dumb because the internet was just making people dumb. So I don't mean to be flippant about AI. Like there are real concerns about this, and it's our generation's problem. It's now like the thing we're freaking out that's exponentially growing out of control for us. But just to situate yourself into context, like pretty much all humans have been freaked out by the technology that was unfolding in front of them and how fast it was going, and they didn't know really what the consequences are. So this is a pretty standard human condition for us to be in. So with this intelligence ladder, and I'm suggesting that this is going to be our horizon model for where AI is going. If you look at these natural systems, if you look at organic systems and how they build intelligence through time, it generally comes through this hierarchy. Most people call this a ratchet or a house of cards because intelligence is not deterministic. It's really fragile. You sort of build these cultural artifacts. But if the culture collapses, those artifacts lose all their meaning and you have lost all that information. So This is not a deterministic process, but it is a hierarchical process. So you sort of always build on what you have before and try to get it as tall as you can without it collapsing. And so the individual, this is the era that we've lived in for the last couple of years with AI. This is we live as an individual in the biological and intellectual space. But there's an individual. You can look across biology and you see lots of individuals that never move up this hierarchy, right? Never get to tool use. But then we have individuals with tools. You see this in lots of anthropology classes, that humans using tools, or now we have crows use tools. In the same article, the same science article, journal, the same week that the stuff I showed you, there is a little inset of like cows now using tools, and that being the sign of like cows now elevating to this next tier of intelligence based on their social interactions. And that is where we are currently with AI. So AIs are currently using tools and they are moving into the cultural space. What do I mean by cultural space? You have individuals that start interacting with each other. So this would be an expansion of all the different ways that these things could interact with each other that eventually collapse into some condensation that we call culture. So that's where we're at with AI, is that it's currently using tools and it's currently moving into socializing and culture. How is that happening? We'll talk about that in the next slide. For humans, after culture is institutions. So something like a cultural artifact would be the sextant or language or something that describes your culture, but is still sort of mobile. And then institutions are where you formalize those. You write the Constitution, you write the Bible, you write some formalization of things that say this is how it's going to be now. And that thing sticks around a lot of it. So again, these are ways to keep memory around. So the overall selective pressure here, regardless of whether it's AI or not, is that memory outlasts not memory. So if a memory is there, then the memory is there and it is competing against a non-memory. And there is a force generally through time pushing us to keep memories. So our ladder, we had genes that collapsed into heritable memory. Those genes then got into cells, which were resilient architectures. Then brains or specialized architectures just for information processing. Once you get a brain, and we'll talk about this with the AI too, you get individuality. So you get this brain and then you get an autonomous unit, and then that autonomous unit has to have a personality, sort of. So I'm not saying AI has a personality, but it needs an identity. It needs that is an AI, and that AI does that thing. Or I'm a person and I do this thing. Individuals start using tools. Those tools are variable, but some of them become symbolic representations. Those symbolic representations start to collapse and define cultures, and those start to define institutions. So we can see this ladder over and over and over again in any system that is accumulating intelligence over time. So that leads us to this horizon model for generative AI. So this is what I'm using to predict where AI is going. I could be wrong here, but this is what I'm using to say, what should we be planning for next year or the year after or the year after? And it's saying, okay, this was 2022, 2023. We get GPT-3. It is an individual. We're trying to make that individual as good as possible, get as high as performance as we possibly can out of the individual. Since then, we've been moving into the last year has largely been about MCPs and tools. Sort of like an MCP is an interface to let the AI use a particular tool. So you would write an MCP for Photoshop or for QGIS or for Excel, and the AI can go to that MCP, and it's essentially just a list of directions on how that software works and how you would operate with it. So it's not straight code saying do this, do that. It's a protocol for what kind of language does this thing use? How do you like to interact with it? What does it do? That sort of thing. In the last year, the last 6 months, we've moved to A2A, which is more than one agent. And so this is still in a pretty nascent phase. You're getting people combining like 2 to 20 agents. And this is where identity comes in. So you have to give each one of those an agent card, so they know who they are and what place they hold in this group of agents. And you need a language protocol, which is generally JSONs. So now you can link these things together, give them each an identity, You're the boss, you do data analytics, you research, and then they communicate with JSONs back and forth and coordinate with each other. This is where you see things like there is a new platform called Maltblog, where it's like a Reddit for agents. And so you give your agent a personality and they go in and only the agents can be on there and they argue with each other and fight with each other and things, right? So most of this is just fun for people to watch. And a lot of people will program like fairly destructive or like trolly type of agents that go in and the agents are just trolling each other. But from a research point of view, I want you to just expand out and think it could be really useful to have agents communicate with each other and talk to each other. Right? You could have a loop of specialties where they all are playing nice with each other. But right now, it's an imperfect science. But it requires an agent card. It requires the thing to have an identity so it knows what it does, and it requires them to have a language. Social structures, again, these are very nascent, right? Like last month or two or three, people are building these things. But that just means we're at the beginning of it. So I think what you're going to see in the next year is a lot of news hype about we put these agents together and they conspired to kill us. And we put these agents together and they came up with like a collective hallucination together. And you're going to see a lot of the stuff we saw at the beginning of ChatGPT as people are like really experimenting in that like variance part of like, let's explore all of the different things that we could do with all of these different agents and how many do we need and this and that and the other thing. But I would expect after we do that for a year or two, we start to get some cultural norms. We start to see like agents really like to talk to each other like this. Agents really they're the most productive when you organize them like this. And we start to learn like some of these social structures that we can give these multi-agent systems. And then those in the very long term would eventually come up with like full internal governance type of structures, right? Like all of the agents eventually agree that they should do it this way. And I'm not saying this is humans telling the agents to do this, but like we get to the place where the agents have done enough interaction with each other that these things bubble to the top. So back to this agent personality. This is the thing that disturbs a lot of people, particularly in these like Reddit type of rooms, is that these things now assume an identity. The identity was given to it by the prompter, but still like that they have this identity and they could take things personally and they could have a viewpoint. And the research that I've seen on this so far is saying like it's impossible to get rid of this. You cannot have a social interaction without these things having an identity. Otherwise, they don't have any way to interact and they don't get anything from the interaction. So the identity has to be a part of that. So as we're thinking again, as researchers of designing these systems, our horizon model, I think, right now for this intelligence ladder is that we're moving from one agent to multi-agents. That is going to go a lot of crazy ways, but you could probably think of a lot of cool ways to arrange multi-agents in a way that's helpful to you. And when you're setting up multi-agents, be expected to be a little chaotic because you're exploring this variance, it's unknown, but that identity is going to need to be in there and some type of norms of how they're communicating is going to need to be in your system as you're architecting. Okay, so Act 2, compression scaling. This is how things got big fast and how they feel magical and how they feel scary. So the idea here, first, these are some repeat slides from the teaching one, but I think that it's so crucial to realize that all of this is growing exponentially. If you hear any of the AI chiefs talk about how things are going, they always use these terms like we're sitting on an exponential or the exponential says this. There's like this figure in the room that's the exponential that's driving everything. And that exponential is the efficiency that we're getting out of the compute right now. It's making things grow exponentially, and it continues to surprise us. It's going to exponentials continue to feel threatening all the time because they're doubling all the time. Like so as you're thinking about this, you just have to go back to the exponential all the time. As you're thinking about what is happening in 6 months, think about it on an exponential scale that it's probably going to expand a lot more than you expect because it's growing a lot faster than you realize. The greatest, I love this. Al Barrett was a CU professor, said the greatest shortcoming of the human race is the inability to understand the exponential function. He just talks repeatedly about how much trouble we've gotten ourselves into, not knowing how this thing works. Here's the XKCD version of that same thing, which is here's how we think things will go, here's how they actually go, and this is our surprise factor is between those. And so you're constantly going to be surprised unless you start thinking about this in terms of exponential growth. Here is the exponential growth of computers through time. And so we are here-ish, where we have exceeded where the standard computer that you have, I guess we just, in 2023, surpassed where the laptop that you have has more compute power than your brain. So you are already in a cyborg era where you have your brain and your equally powerful brain in front of you all day, every day. That is just going to keep going up and up and up. Your computer is going to continue to be more and more powerful. You're going to continue to collaborate with it, but just know that it now has more compute power than you do. This was also from the other slide showing that these things build on each other and come in waves and also get faster. So again, here we are in this third wave of AIT and Internet of Things, robots and drones. And just the expectation is, again, exponential growth. So as we're thinking about a horizon model, it's multi-agents and it's really fast growth, like rapid improvement of how good these things are. Okay, so where does that scaling come from in these artifacts? This is the compression of information. So down here I have that I take a note to myself, and I have essentially compressed the information in my brain down 1,000-fold. So I write down a little note, the language, the sort of bits of information that are in there is something like 1,000-fold compression of what information I have in my brain. So that scale is actually relatively close to each other. It's like I'm condensing information from my thought onto a note, but they're relatively similar scaled to each other. So it doesn't feel that magical. It feels like the note is fairly representative of the thought. Here we are at LLMs, where we've gone up 9 orders of magnitude in terms of how much information is compressed into one idea. So if I do a prompt and get an answer, that answer is coming from the collective intelligence of the entire internet instead of my note coming from my brain. So we can show things like Wikipedia is a couple orders of magnitude below that. A normal book is a couple orders of magnitude below that. So a book is a big condensation of information. There's a lot of information in a book. And it's different. There's a differential between how much information is in the book and how much is in your brain. And so you read a book and it usually feels surprising and new and feels like there's a lot of information in there. This is a big difference between the content and the compression coming down to you. Now jump that up several orders of magnitude. Just the amount of raw information that's being condensed down to you is really impressive. So you're going to lose stuff. There's a not a lossless compression. It's a lost full compression. So as AI gets bigger and bigger and bigger and goes up and up this chain, it's compressing more and more information down and down and down and down. It's going to lose more. It's going to need more condensing so your brain can understand it. Right. So your brain's at a particular scale, and this is above that scale. But it's still locked at the scale of the internet because that is all of the training data that we have for these things right now. But there's still a physical limit, which is way, way, way higher. So this is like the physical limit of data storage in the universe at 27. So here we got like 15 orders of magnitude, 16 orders of magnitude difference that we could still go. So, and we're growing exponentially. So now you imagine something on the orders of 10 years from now, when we've moved farther and farther up here, the reason it's feeling so much more powerful is that it's condensing so much farther to get back down to your brain. So we're getting more and more and more information, higher levels of information, higher dimensions of information, and it has to come way farther to get all the way down to us. That makes it feel more magical. That makes it feel smarter. That makes it feel like a bigger intelligence. But really, it's this like how How different are those scales? How much bigger is the raw information from your brain? This is back to that Nature paper talking about the condensing of citations, which talks about, which tells the same story that we were just telling. So the blue line is projects without AI. What are they citing? And they're citing a larger breadth of the existing literature. They're getting out here into the weirder papers that have the crazier ideas and the less normalized ideas. And the AI shrinks that down. You sort of cut off all of the sharp edges and you wind up getting the central tendency a lot more. But this is quantifiable. I mean, they showed it was something on the order of 20%, 22%. So the condensed, this sort of the condensation of the whole internet is roughly 20% into that final model. The way these are all stored is in a multidimensional space. So they're given spatial relationships to each other, and we can draw lines through those and separate them with different lines, or go to a particular part of the space and sample from that part of the space. So this whole thing, this whole machine, when it's condensing, the way it's condensing, the structure that's condensing down into is a multidimensional space where everything's related to each other. And so you actually get spatial relationships. So here is king and man, and if you shift in this direction, you get woman and queen. Here is walk and swam, and you shift this direction, you get walking and swimming. So these are language relationships, but they're showing like the spatial location in this hypervolume is showing the relationship between ideas. And that is the actual structure we're using to condense this information. So as you're a researcher, again, let's think about all of the ways that you've used spaces like this. You use PCA, you use orthogonal stats. These are just extensions of those tools that you've already used in your own cases. And they're just stuffed into these big complex machines. But under the hood, all of it is sort of the normal stats that you guys do in everyday life. We are going to just, since we're in the scaling section, do a little detour, I guess, about sustainability. I don't really know, next week we'll talk a little bit more about this and how to use AI. But I just wanted to point out that there has been this really rapid change in how the sustainability community feels about data centers. So for the last 20 years, I've been going to lots of sustainability conferences and sitting in sustainability talks. And there was this general theme of like, data centers are the future of sustainability. They're more efficient per unit time. There was this, like, going into it, lots of people had server rooms in their own labs or in their own companies or even in their own houses, which those are inefficient electricity wise. They're inefficient distributed like that. They create a lot more e-waste because you buy the thing and then throw it out. You don't have this standardized form. So there's been this big push that like data centers were the answer. You get a community that wants one of these and could use the economic development. You now have a good place to build it. You build the thing, your now efficiency per unit flop goes down, and your e-waste goes down because they're all the exact same thing. And the vendor is motivated to like have to change those things out, and they're left with all of these like totally identical e-waste things, and it's easier for them to go to recycle them. This was the discussion. Then the exponential curve started freaking us all out, and we started building data centers super fast. So again, if you looked 5 years ago at building data centers, most of these data centers want a month of reserve of power so that they never go offline. So if by chance they lose their main source of power, they can just run themselves. 5 years ago, this was all solar panels, batteries, maybe some gravity batteries to hold that in, wind driven. It was all like renewable backup power. Now the boom is going so fast, nobody can get any of the parts. There's big backlog on everything. People are just building these things as fast and as cheap as they possibly can. And so now it's just like diesel compressors with like 1 million gallons of diesel fuel on site in case this thing goes down. So there is a lot of heterogeneity in the market here, right? There are data centers that are really nicely built and efficiently built and are well jiving with the community and are doing all the things. And then you get these things that are popping up really fast and are really inefficient. There's an associated like lending crisis in the background there, that people are building these things that cost $300 million and most people don't have $300 million. So companies like Oracle are just they're borrowing like trillions of dollars to build these things fast, trying to keep up with speculation. Again, because the exponential growth, you just don't know how many you need. So as you're thinking about these things, I want you to just not think about it being a monolith. I want you to think that like most of their water consumption is non-consumptive. It's mostly cooling ponds, and you get some evaporative cooling, but most of them are using, you get some of Elon Musk's things where he's using these like water jet things that are really consumptive. But again, it's not a monolith. You're getting some really good actors and some really bad actors. The last note here is just about scale, right? Like AI is currently about 15% of all data centers. And most of that is still like e-commerce, iPhotos, Facebook, just our general digital life is also filling up these things. And they're generally pretty efficient. The big problem is that they're additive. So it's like electric cars were displacing combustion engines. So that was a positive move. And so even if you're putting a bunch of energy into destructive extraction of lithium and building these things that didn't exist, you're trying to displace some higher carbon thing. AI is not displacing anything. It's just new. It's just a new use. So it can be really efficient. Like the stat I've been telling a lot is a roast beef sandwich is roughly 65,000 prompts. So the scale here, like the classic meat consumption problem of environment, is still orders of magnitude bigger problem than AI, but AI is growing exponentially. The budget for next year is something like $1.2 trillion in new data centers just between the two big companies. So with exponential growth, you see this thing take off. So I don't really know where this puts us. I just wanted to, I guess, bring up that there has been this sort of massive switch in how particularly the sustainability community is feeling about data centers. And I do sort of question about whether we found the right enemy to pick on. Like it's bad in lots of ways, but to me that like digital divide inequality thing that we showed at the beginning is a little more concerning even at this point, because we're losing lots and lots of people who are not benefiting from this. But I think that's a good conversation for us to have later. I think the main question comes down to these things help us predict, and those predictions could have benefits. But they also have some risks in this infrastructure that we have to build. And we need to have this new conversation about like, what can we do with this thing that is useful and how much are we willing to spend on that, and try to not use it for things that are not useful. Okay, the last act is autoregression. All of the AIs that exist right now are autoregressive models. What is autoregression? Autoregression is just predicting what is about to come based on what has happened in the past. So again, we have this through history. We get first sensory motor skills, just the ability to sense and interact with our environment. That is a predictive quality of biology. And so it starts with a relatively high quality of prediction for a relatively low cost. Now, episodic humans, these are things like we start counting how much agricultural production we have. We start counting how many people are available. We can start counting when people die and when they don't. We start realizing that the spring is when things bloom. And that gives us more predictive power. Symbolic culture, we build a lot of artifacts that help us transmit that memory from generation to generation. We eventually invent mathematics, which helps us then formalize all of this stuff. Then we build computers, which helps us predict it even more. And we eventually get to LLMs, where we finally get this cross in prediction quality versus prediction horizon. So LLMs have a longer prediction horizon because of that massive condensation. They have a longer horizon. They can predict farther into the future, but our quality has gone down. Our quality of prediction has gone down. So I think you're going to see a lot of pressure in the industry to get those predictions up, and that's what you have seen. We're just trying to get like prediction better and better and better. But part of the problem with, as researchers, we get a lot of guff for accuracy. Like we need things to be right. We need things to be the way they really are. And so this predictive horizon of LLMs is part of why people are freaking out about them not being great scientists. So I think that those things will switch, but right now we have this problem where LLMs have a longer prediction horizon than they have a prediction quality. Autoregress, this is like what we use day to day. This is from the summit last summer. This is a thing that I made for the analytics library. We were just using autoregression to predict climate into the future and see where tipping points were. This is what the LLM is doing. It's taking the data that it has and it's predicting data in the future based on what the trends are that it sees in the existing data. Where does this matter for a researcher? This matters a lot because you sort of assume that it's using all of this pre-existing data every prediction. But your prompt makes a really big difference. So we'll talk about this next week when we do the how to do this thing. But really, like how you set up the prompt tells the LLM which information to auto-regress, and that affects the prediction a lot. So you can get much better predictions if you give it better prompts. Most of you have heard of Markov chains, MCMC. This has been the classic way of doing Bayesian statistics. And Markov and Markov chains are a central integral part to LLMs and to all the AI. Markov, actually, his very first paper and the one that invented the Markov chain was him trying to predict consonants from vowels. So he was in language trying to predict future tokens of language. So he sort of invented this whole LLM thing 100 years ago, 110 years ago. And that same Markov chain is exactly what we use. They just have been built into these large machines where you do it gazillions of times, but you're still optimizing the same way. Okay, this is a perceptron. In 1956, I think it was, this was the very first AI was invented, and it was built entirely mechanically. So here we have power comes in, and you can switch on and off. So this would be one bit of information like in a computer. And so that's your network. You can turn those on and off. You can then tune the power that comes out of that and try to make this always positive or always negative. So the idea is that you're predicting which one of these outputs comes by what your inputs are. Now, this topic, the thing that I want you to get from this is this idea of what we call linear separability. So that whole thing is making a line. All those knobs make a classic mx plus b equation of one line that would try to separate all those dots. So the point here is that you cannot train an AI that small to capture all four of these dots. All you can do is draw one line in between them and divide two dots from the other two dots. Or try to go find some complicated orientation of the line where you could separate it. Right, so here are the four possible orientations and whether I can make them positive or negative. And right now, these two don't match up. The line that I've made separates the bottom two dots from the top two dots, so I can't get this. So this was the very first big problem in AI, was this problem of linear separability. It's like, can you draw a line to separate these two things out? And it turns out that with one, you cannot. And the answer is to go to many. So here we do two neurons now. That's the one perceptron, and there's one perceptron, and you can add the two together, and that gives you two lines. So now with two lines, you can separate more. You can say these two come out or these two come out. It gives you more power. So we go from two to many. So this is still one layer, but we can add a lot more knobs. So that gives us more lines to start separating. We can layer those things. And then So that thing that I showed you is part of both of these. These are the two building blocks of a modern AI. First one, multi-layer perceptron. This is 3 layers. Just to get 3 layers. And then an attention block pays attention to how much change there is between 2 layers. So those 2 main parts, you get this perceptron, which can take inputs and give a nonlinear output, and the attention block, which says which things should be adjusted and which aren't, which shouldn't. Those just get stacked and stacked and stacked and stacked and stacked. So for something like a ChatGPT, you get somewhere on the order of like 10 million of these layered into something like 100 layers. You skip that's what they look like, but we don't care. And then here is our surface. It's called our loss surface. So back to the Bayesian thing. A lot of you that have fit Bayesian parameters, you wind up getting this sort of squiggly surface, and you try to find where the parameter is at its minimum. And often you found that there could be a local minimum that is not the global minimum. So there is the lowest point for the model over here, but because it goes up and down and up and down and up and down like this before it drops down, as you're traversing the parameter space looking for that lowest point, you find a bunch of lows. And it can be really confusing whether I'm in the bottom or if I should keep going and find the all the way bottom. LLMs do this exact same thing. They use this technique called gradient descent, where if you dropped a ball right here and let it roll, you try to let it roll all the way down and fall in the hole in the middle and find its lowest spot. Same thing you would do with the Bayesian thing. And so what you do is you let the ball have a particular amount of momentum. So if it goes in, it tries to come back up for a certain amount of time. And if it finds another low, then it can go down. And so you let this thing travel farther and not get stuck in local minimums. That was like it took like 30 years for AI to discover that. So this was the big hurdle for a long time. The guys that invented the twisty knob thing, there's a story of like these 2 grad students think about gradient descent. They go home, they like stop at the electronics store on Friday night on the way home from campus. They buy all the stuff, they build one, they spend all weekend trying to do this thing. And they couldn't get it to happen because those knobs wind up getting these discrete drop-offs. And you wind up getting this like discrete drop-off and you can't integrate the gradient, and you wind up getting this like integration error and it fails. And it took a really long time for people to just figure out these few simple parts of getting the integration to go properly over the gradient so that it didn't get stuck and could go all the way to the minimum. And now everything works like this. So here is not a full network. We can't put the whole thing. Just imagine we have a few more layers going this way, and we have about 1 million more nodes this way. The information comes in one side and makes a prediction on the other. We've talked about transformers, lots of different architectures of this. A transformer specifically has the same list of words in the input and the output. So it can't create new words. It has the same library, and it just says how, given this library, what is the next word out of the same library? So the transformer architecture always just has those 2. So when we train, we first are going to give it, so the capital of France is, we would give it some number of vectors. Those propagate through. This is just, they're doing the math on what the probability is of each one of those things is. And it picks some thing. Here it's already picked Paris, but imagine it picks some other word. Then we get what's called back propagation. This was the next really big thing that unlocked the AI card, was that from whichever one I pick, we say, well, that wasn't good. For it to be the right one, how would I need to go and adjust everything back? So all the blue lines are after we pick Paris. How does it then back propagate to go and adjust all the weights? And so to train, you forward propagate, back propagate, forward propagate, back propagate, forward propagate, back propagate. And that whole time it's adjusting all the weights and trying to come up to where, according to your training, it's giving you the best prediction. in the output based on the input. Okay, so the mental model I want you to have here is this is the same as MC chains that you've been working on your whole life. It's just an extension. They've just been built into bigger things. And the two really big breakthroughs that allowed AI to break out of its 50 or 60-year slump was first, second was propagation. Oh, first was gradient descent. Yeah. So first was how to actually use calculus to figure out the gradient descent instead of your exact your exact latitude, altitude. And then the second was back propagation, which is a way to adjust all the weights based on what answer you wanted to have. We are running a little out of time. Okay, so here we just have three. We're going to move into we don't need to do that. In 2D, each one of those lines you saw, and we just drew a line to divide stuff. Here we can do full planes. So as the data get more and more complicated, we're doing that same cut the data with planes. The more planes that you add, the more you can cut it up into smaller pieces. So if you were trying to make a polygon, if you had a really simple polygon, you would not need very many planes to distinguish that polygon. As it becomes more complicated, you just keep adding more and more planes, which are more and more cuts to the data. And this is why we wind up getting these huge systems. So to leave you with your mental model. Okay, so first, intelligence scales by externalizing persistent memory. So this is a really big part of any one thing in all of biology and all of history could have been pretty smart by themselves. But unless they created something to pass on, none of that is seen as intelligence and none is passed on. Because they pass those on, intelligence has gotten bigger and bigger and bigger. It's physically scaled, and we get structures now that can fit more information in there and condense that information more powerfully. Number two, the power of predictive system depends on the scale separation between the input and the stored memory. So again, my feeble brain compared to the entire information content of the internet, those two are widely separated. And so something that can condense the entire internet feels more intelligent, feels more powerful, scales a lot bigger. So as we keep going bigger and bigger and bigger, they're going to feel more and more impressive because they're funneling more information down to us to the same small size. And number three, as persistent memory grows and compression scales, the predictive horizon expands. So the reason that we keep using these things is we keep getting longer and longer predictive horizons. Those have really good quality right now, but the quality will get better. So the idea is that we get better predictions at longer horizons, which lets us maybe overcome a lot of the ills of AI, maybe not. But that's we can at least articulate that that's the benefit that we should be getting. So with that, I can have 5 minutes for questions. Thanks, guys. All right. Questions, comments, concerns, arguments to be thrown? Yeah. Yeah.
But I have a question about your analogy with the roast beef sandwich.
Yeah.
Is that in terms of water use or overall
carbon storage? Yeah, carbon footprint. Totally. And you get this so there's the amortization cost of anything and there's the single use cost. And so people love to conflate these two of the amortization cost is how much did it cost to make? What is all the R&D cost? Do you fold that in there? And for LLMs in particular, that is the majority of the cost. So if you don't amortize and you look at just the single use inference cost, it's remarkably efficient. And so meat, we often don't amortize that one thing. We just look at the end consumption. And so even non-amortized, you look at those two things, meat uses a ton of carbon and a ton of consumptive water use and is 4 or 5 orders of magnitude larger in scale than neurons. Yeah.
In terms of scientific research, how do you differentiate with your mental model between LLMs as a tool and like deep learning Earth foundation models as the product you're building.
Yeah.
Because I guess most of this seems to be like how we like use LLMs to like become more efficient.
Yeah.
But there's also like the shift in, you know, what we're creating as researchers
Yeah.
also being wrapped up in AI.
Yeah, for sure. So to clarify, there are a lot of different architectures that are not transformers. So a transformer takes one library and converts it to another library. Convolution neural networks will take a large flat thing and it'll cruise through it and condense it into smaller things. The foundational models might have something like physics informed versions of this. So I think there is a lot to be done with different architectures in terms of answering specific questions. But those are pretty technically involved ventures for people. You sort of like need to be pretty deep in the weeds to like go make your own network. What I think is going to happen for the average scientist is that the LLMs are going to be their bridge to even doing that more complicated stuff. So you would use the LLM as an agent to help you code up the new thing, and then you use the other thing to use it. Or you go build the thing and then you use LLM to do the documentation, describe what you're doing, something like that. So I think that it's going to be this like mixture of architectures thing. And there's going to be a push in both of them, but the LLMs are so big, they're sort of out of the hand of the researcher. A lot of our job there is like, how do you use them properly? How do you know what they're good and bad at? And then how do we use them to do what we're talking about? Just like more bespoke design of things that are really targeted towards science question. Does that jive?
Yeah, that's what I think.
Yeah, go ahead. Yeah.
Very good stuff.
Thank you.
So, yeah. So my question is, so you have figures that have citations with and without with the AI, it has this citation bounds. So do you think AI, to some extent, might also limit people's intuitions in a way? Because it might cite more proper things than humans are trying to randomly idea. So, you know.
Yeah.
But will you give us some limitations when just like.
Yeah, 100%. And I've noticed this in my own work. Like if I come up with a pretty crazy idea and I ask the LLM, it does not think that that is part of its universe ways of thinking about things. And I think that's where humans in the loop like really are continuing to be really additive to this whole process. The LLM cannot think outside the box. You can. It does not walk around the world in an observation state. You do. So there are all these places where you're going to see places to push the boundary and go beyond the LLM. And that's where you're going to have to make new stuff or get agents to work in new ways so that they do what you want them to do and stuff. But you're 100% right. I think that's where we continue to add a lot of value to this whole thing.
Maybe jumping off on that, how do you feel about this condensation activity as a bias creation engine, specifically propagating the already existing societal biases that exist in research, that exist in technology to, whether it's, racial bias amongst or regional bias amongst research that we read, gender bias, et cetera. How do you push past that if the engine is condensing towards that societal need?
Yeah, totally. I think in humans, you see this in the variance in culture, right? Like their cultural evolution has been going a long time and everybody's condensing their ideas in their own way. And you wind up condensing around your own biases and differentiating cultures, and you get like divergent trajectories over time. So I think you'll probably get that, and it'll just be faster because there's more opportunity for more variance, more different condensations. That's the thing. So 100% right. Like it's a big problem. We talk a lot about it in like our tribal engagement work, that they're like the Lakota language is not very represented at all. And when it is represented, it's poorly represented. And so there's now like a bad and like it's low information and bias, bad representation of it.
So I think this is something we need to tackle for sure. I don't have a right solution there, but,
Solving the world's problems today.
yeah, they're really good. But yeah, I think the writing's on the wall that there's gonna be a big divergence in. You just look at like Elon Musk's version versus OpenAI's version, or like a lot of different. All right, I think we're out of time. All right, thanks, guys.
See you next week for playing with it.